everyone, and welcome to another video of our channel Science Matters. My name is Trina. I'm an astrophysicist and an online coding instructor. I like to solve complex and fundamental astronomical problems just using the math and physics knowledge from high school. And I like to show my students and all kids all over the world how incredibly easy it is to solve and encounter any astronomical problem if you have a solid understanding on high school math and physics. So the problem we are going to solve today is how to calculate the distance to the horizon. So how do we define horizon? Horizon is the point in your visual limit where the curvature of the earth really seems very obvious. So the sky seems to meet the ground. So if the earth was a completely flat surface, and if a person was standing anywhere on the earth, they should have seen up to infinity because there would be no obstacles in front of that person. However, that is not the case, as Earth and any other planet or celestial body in our solar system or somewhere in the universe which is rotating, they actually have some form of curvature. So, for a curved surface like our planet, if you are standing anywhere on the surface of the Earth, there will be a limit to how far you can actually see. So the curvature of the earth will block your vision. So I'm going to solve the problem of how far you can see. There are two different ways to encounter the problem. First method, I'm going to try with a very geometrical approach, and this is really easy. So I'm going to try to draw a very spherical earth, and here you go. And let's say this is the center of our earth, which I can denote by O, and I'm going to draw a line up to the surface of the earth where a person is standing, and the person is just trying to see. Okay, so this is the eye height of the person, and I'm going to draw a tangent from the eye height to the person, and that tangent is going to meet the surface of the earth at this point, let's say D. Now you all know by the rule of geometry, if you try to draw a tangent wherever it touches the circle, it actually creates a right angle if you extend that line up to the center of the circle. So you already see that I created a right angle triangle, and the distances are known. The distance OD is actually the radius of the earth itself. Now this distance O to A is again the radius of the earth. However, you also have to counter the height of the person, and the height of the person I can say H, and the height would be known, right? So for average humans, we consider the height to be 6 feet. So let's say I call the whole distance OB to be R plus H. So as you see in the right angle triangle OBD, I already know two sides. I know the side OD, and I also know the side OB. And for right angle triangles, we can only apply Pythagorean theorem to find the other side very, very nicely. Now here, the distance BD is our point of interest because that is our visual distance to the horizon. So I'm just going to apply the Pythagorean theorem to find the distance of BD. So for this angle OBD, I can say OB squared equals to OD squared plus BD squared, which is still unknown. And let's try plugging in the numbers. So for OB squared, I can say R plus h whole squared plus OD would be, equals to OD would be R squared, and BD squared is still unknown to us. And here I would like to expand the R plus H whole square, which is R squared plus 2RH plus H squared. And I would like to take this R squared here as well on the left hand side. So on the right hand side, I only have BD squared. Now, as you see, this R square and R square cancels out. All I'm left with, I'm gonna do it here, BD squared equals to 2RH plus H squared. Now, you should remember that in terms of square or cubic, if the h is very, very small compared to the radius of the earth, then you can actually omit the h squared. But you should not omit h squared if h is very high. In case, let's say, you are trying to measure the horizon of the earth from Mount Everest or from a very tall building, in that case, you should keep the h squared. But if that is not the case, if h is very, very less than r, then you can just say h squared goes to 0. So you are left with BD squared equals to 2RH. That actually implies the distance BD equals to square root of 2RH. And all of these are known quantity because r is the radius of the planet Earth and h is just basically the height of the person. Now I'm going to just give you all the numbers so you can plug in the numbers and check. Make sure that when you are doing this calculation, you are converting all of those numbers into the same unit. So the radius of the Earth is around 6,400 kilometers. And average height of a person can be, let's say, 6 feet. And if you consider all of those into same unit and do the calculation, it will be around 4.8 kilometers. So that's it. If you are in a deserted surface where you have no obstacles in front of you, you can actually see the farthest to be 4.8 kilometers, and that also applies to your behind and to your surroundings. So anywhere you see, it's gonna be exactly 4.8 kilometers from where you're standing. So this is the first way of looking into the distance to the horizon, and this is a geometrical treatment. However, there is another way of solving this problem, and I'm going to talk about it in our next video. Thank you very much and have a great rest of your day.